Swayam Prabha. Digital India. Educated India.
So as you can see, because of this zigzagging nature of the steepest descent method, actually is the main reason why for it to be slow, and it will be slow when the condition number is large. So what we can now think of is, okay, we need a method, as I mentioned in the previous lecture, we need a method that takes into account, that doesn't simply follow the steepest descent, but rather takes into account also how this direction itself is going to change, right. So it must take into account not only the gradient, which tells you the direction of the decrease of the function, but also how that gradient itself is going to change, which is now that the way the gradient itself is changing is captured by the curvature of the function, or in other words the Hessian of the function, right. So if we have a better method would be one that takes in that knows at this point itself that although this is the direction of steepest descent, I should not actually be going here, because this is not really a sustainable will not give me a sustainable decrease. I would have to again change my direction and go in another direction, etc. So what we would need is ideally a method that while you are sitting here itself identifies, looking at the curvature and all this other information, identifies a better direction to move in. Okay. And that is what is that method is basically Newton's method. So that is Newton's method. Okay. So it's again a method like before, but now we are going to take what we are going to do is take a Newton's step. So P Newton at time k, at iteration k, is defined in this way. It is defined as the Hessian of at x k defined as the Hessian of x of the function at x k inverse gradient at x k. Now here's one important thing to note. See, the Hessian itself may not be positive definite. Okay, so Hessian need not be positive definite, and in that case the Newton step or the Newton direction may not actually give you descent. Okay, so the Newton direction may not be a descent direction. May not be a descent direction if this is not positive definite, right. So as a consequence, a lot of what we discussed so far does not actually directly hold for Newton's method, meaning that we are not necessarily decreasing at every step with the Newton's method. We may not even be getting descent, we may in fact be getting ascent, we may be increasing the objective value, right. So so when applying Newton's method, we have to be careful that we are actually although the method is intelligent in the sense that it takes into account the curvature of the function, we have to make sure that that we are in fact getting descent, right. So, okay, so let us now discuss the rate of convergence of this of the Newton method. Now, one other thing I want you to note here is in the Newton method is that the Newton step is itself has baked in it already the step size. The step size has been has already been found for you by taking into account the curvature of the function through the Hessian. So, one does not usually need, in addition to this, another step size. Because the Newton step is a complete step, meaning that it is not just a direction, it is a complete step to the next iteration, right. Okay. So, here is the theorem. So, suppose f is twice continuously differentiable and the Hessian at x is Lipschitz continuous in a neighborhood of x star at which the sufficient conditions of optimality are satisfied. Now, what does this mean? Sufficient conditions of optimality are satisfied. It means that it is a point at which gradient is equal to 0 and the Hessian is positive definite. Okay. So, that means the sufficient conditions of optimality are satisfied, and consider the iteration. So, let me write this for you in the bracket. Uh, so, the gradient at x star is equal to 0 and the Hessian at x star is positive definite, right. Consider the iteration xk plus 1 equals xk plus pnk, where pnk is as defined above. Then, if the starting point x0 is sufficiently close to x star, then xk converges to x star and the iterates converge to x star. Moreover, xk converges to x star quadratically. That means, if you look at the error between xk and x star, that error decreases to 0 quadratically. And third, if you look at the norm of the gradients, this norm of the gradients, this also converges to 0 quadratically. So, let's take a note of a few things. So, I mentioned to you, let's see what the theorem is saying, that if f is twice continuously differentiable and the Hessian is Lipschitz continuous in the neighborhood of x star at which the sufficient conditions of optimality are satisfied. That means it's a local minimum of your function f. And you look at this iteration, which is x k plus 1 equals x k plus p n k, where you are taking a Newton step. Now, here's the main thing. If x 0 is sufficiently close to x star, then you are guaranteed that this will converge to x star. That means, if you are sufficiently close, what does this mean? You are in the neighborhood of x star, means around you are in a part around of the space around x star, where the function f looks convex. See, if the function may very well do other things elsewhere, but around x you are close enough to x star. So, at x star the function has gradient equal to 0 and Hessian positive definite. So, in a neighborhood around x star, the function is actually convex, and what this is saying is that you are starting your iteration in that sort of neighborhood. You are starting your iteration in a region where the function is convex. If the function is convex, then in that case, if you look at the Newton direction, in that case, that means if the Hessian, then if the function is convex, then the Hessian actually is positive definite, right. If the Hessian is positive definite, this is actually then a descent direction. And then, so if you start your iterations in this sort of region, then the Newton direction is a descent, gives you a descent direction. Okay. So what does this theorem say? That if you start your iteration somewhere close enough, then the iterates converge to x star. Moreover, they converge quadratically, and even your gradient vanishes quadratically. The norm of the gradients also vanish quadratically. So if you start your iteration somewhere in this sort of region, then the Newton method not only converges, it converges quadratically. It converges faster than the steepest descent method. So the main thing here is that because the Newton direction is not guaranteed to be a direction of descent, we have to include this rider that you are starting in this kind of basin of attraction, where the function is actually in a neighborhood of the true minimum, where the function is convex. Now, if the function actually is convex everywhere, then things become easier, and then this sufficiently close really has no bearing on the final result. But the main thing to note here is how we've got now quadratic convergence as opposed to linear convergence, which is what steepest descent was giving us. Now, so we can also do other variants of the Newton method. So one can do, for example, instead of taking in situations where the Hessian is not positive definite, okay, one can come up with variants of the Newton method that tend to mimic the behavior of the Newton method. So, for example, you could do simply Pk equals sum minus Bk inverse gradient of f at xk, where Bk is symmetric and positive definite. Right. So, Bk is symmetric and positive definite. So, this kind of iterate is what is called a quasi-Newton method. Quasi-Newton method. Now, what this tends to do is it brings you a little bit of information about the curvature alongside and also gives you the properties of guaranteed descent. Now, the way the Bk is obtained is through the past derivatives and past information that you have obtained about the function. And so, there are many different ways of of updating this BK, one of the sort of most popular updates is what is called the BFGS update. So, we do not have the time to go into all details along all this. The BFGS gives you a update, it gives you a way of updating method for, it is a method for updating. Updating BK. Now, what sort of result can we get for this kind of a all right. So, now with having so now with this, I think there is this gives us a wide gamut of methods for solving unconstrained optimization problems. So, from here now we will move on to constrained optimizations.